Okay, welcome guys. It is my pleasure to introduce Jonas Latz from Manchester. Um, he's in applied mathematics at the University of Manchester. His research is at the interface of statistics, probability, numeric analysis, and computer science. And he has a lot of interesting research. For example, the one we just talked about, can physics inform neural network beat finite element method, and a lot of other research on stochastic analysis. So uh, I'm really looking forward to his talk today about losing momentum in continuous time stochastic optimization. The floor is yours.
Yes, thank you very much for the invitation, and I'm very happy to talk a bit about this paper. Um, so actually, wait, did you see moving the slide switching? Yes, probably.
Yes.
Yes, excellent. Okay, so first of all, there is a paper connected to this talk, actually kind of two papers that I will mention. The first one just appeared in JMLR, like in the end of last year, and then there's one that's a bit older, in stats and computing. And the first one is is jointly authored with my friends here, Akesh Jin, who recently graduated from Princeton, Shenggang Liu, who is a postdoc at Delft, and Alessandro Scagliotti, who is a postdoc in Munich. And there's sort of some other works that sort of broadly fall into this. If you're interested in these, then please just let me know, or you can check my webpage, and I can kind of guide you through which one you should read if you're interested in this. By the way, if anybody else wants to switch on their camera, please feel free to do so. I think it's recorded, but it's always nice to see some faces when giving a talk. But if you don't want to, that's also fine. Okay, so just give you like a brief outline. So we'll first talk a bit about optimization and data science, because obviously we're trying to lose momentum in optimization, and I will kind of just motivate what we want to optimize here. And this might be, if you work in machine learning, then this will be already trivial for you, but let's just kind of start at something we all understand. Then I will talk a bit about classical mechanics, and you will notice that I don't know a lot about classical mechanics, but I kind of just know enough to sort of highlight where we use classical mechanics to understand optimization. And then I will talk about sort of like a continuous time version of some gradient-based stochastic optimization methods, which will be called stochastic gradient momentum process. And then also kind of some theoretical analysis of that we did, and why this is important, and things like that. And then we actually implemented this, and I'll show you some details with implementation and some experiments, and then there will be some conclusions. So now my issue is I'm in the UK, so it's kind of late here for me, and I'm an early morning person. So I'm not sure I will make it to the conclusions without falling asleep in the meantime. So I just kind of give you the conclusions already. So we have those done already, and then kind of if I fall asleep, it's not too big a deal, and we can kind of continue this talk in a few hours when I'm awake again. So optimization data science is difficult because of big data and non-convexity. Yeah, big data in machine learning problems and non-convexity of target functions. We use classical mechanics because optimization methods can sometimes be studied through classical mechanics. The stochastic momentum process will be used to explain momentum-based stochastic optimization. It can be used to approximate sort of other stochastic gradient type processes and gradient flows. And what we will see that if it loses momentum, it can actually find a minimiser in a strongly convex optimization problem. So you see the hypocrisy there already. And then if discretized properly, this process is actually great for convex optimization and also for deep learning. Okay, all right. So let's get started. Throughout this talk, we will always think of a minimization problem that looks like this. So we have some function phi bar they want to minimize, and this function phi bar is just given as a sample mean of other functions phi I. Okay, we minimize this just on a space X, it's just R to the N, and we assume that these phi i's are always like sufficiently smooth, like say continuously differentiable or so. And of course, you've seen problems like this like of this type before. Yeah, so you can think of negative log likelihoods or loss functions or misfits, kind of depending on the community you are in. We may have different names for that. And these like phi i's will just represent certain data subsets usually. Yeah, and so that's why we often refer to methods here as like subsampling methods. Yeah, and I'll come back to that in a moment. Okay, so why do these appear? So you can think of image reconstruction, for instance. Yeah, so that was like a Hubble picture in the early 90s, late 80s. It was very blurry because there was a problem in the Hubble mirror, so it produced blurry images. And then Hubble was actually fixed. Yeah, so they kind of put glasses on top, but obviously that's kind of expensive. So a question could be is like how to get rid of the blurriness in the picture on the left. And what you would do maybe is a variational inverse problem. Looks a bit like this. Yeah, so here Ci is some blurring operator, or C is some blurring operator. You apply this to the image, you subtract the data you have, and you try to minimize that. And then probably add some vectorization that leads to sharpness in the image on the right. Okay, and that's just a really classical thing. And there you have this structure where you kind of need to minimize like a big sum of many, many things. So here it would be sum of all pixels maybe in this image. All right. A difference I think that you might be more familiar with could be supervised learning. So where we say, okay, we have some sampled x's and y's, and they have a joint distribution, and you would like to learn to predict y from x. And yeah, so actually find a function that kind of predicts that and kind of find this function by using some finite data set of these pairs, x's and y's, and some parameterized family of functions f hat. And then we sort of minimize the distance between some loss function, or so I want to call it, to find parameters for our big family over all these data sets. And then here the sum would again not be pixels, but would be all of the cat and dog photos or whatever it is, or maybe yeah, you could think of like cipher 10 pictures or so, and then you have outputs and inputs and labels, something of that sort. And then you might use something like deep neural network, but I mean, you've probably all seen that before, but that's a bit how it looks like. Yeah, so you have some finite sequence, and the sequence is always given as some nonlinear operation and some linear operation, and the linear operations are the ones that give you your parameter. Yeah, so the parameter theta is just a big combination of these matrices and vectors. Okay, anyway. Now, how do we minimize phi bar? And we kind of said that phi bar is sort of, say, continuously differentiable or so. So what we might just try is a method called gradient descent, where we just follow the following iteration. Yeah, from the current position, we get to the next position by walking into negative gradient direction. Okay, because gradient direction gives us the steepest ascent, so negative gradient direction gives us the steepest descent. And we sort of believe that by always going to the direction of steepest descent, we would find the minimizer. And that's actually true, for instance, if phi bar has a minimizer and is convex, and if these step sizes, eta k, are chosen sufficiently small. There's like a million different convergence theorems for gradient descent. I mean, this maybe is one of the simpler ones, but there's a lot that can be said about this method. What could possibly go wrong? First of all, this number n could be large. Yeah, and when n is large, that actually means that we don't compute one gradient of phi bar in every step, but we kind of compute n gradients of the phi i's in every step, and we sum them up. Yeah, and if n is like 10 million, then this might not be possible. The other problem is phi bar could be non-convex. Actually, in deep learning, it's pretty much all the time non-convex. In imaging, it is usually convex, but there are also imaging types where it's non-convex. So we can't hope for convexity in those settings either. Yeah, so n could be large. I mean, okay, I mentioned deep learning already, but could also happen when you have like, say, like astronomical images or so, that where one image is a couple of terabytes in size. Yeah, then you might not be able to use even simple image reconstruction methods. Yeah, just because n is too large. Okay, what do? We do a stochastic gradient descent. Yeah, and so here the idea is just, instead of using the gradient of phi bar, we just pick one of the phi i's, yeah, at random, or like a few of the phi i's. I mean, it doesn't really matter for this talk. It would reduce your variance, so you should probably take more than one. But you just say, okay, we just do our normal gradient descent step, but instead of having phi bar here, we pick uniform at random one of the phi i's and do a gradient step with respect to that phi I. Now this converges, for instance, also there's like a million different convergence results, but convergence, for instance, if the phi i's are strongly convex, and the learning rate, so this eta k is now suddenly called learning rate. I'm not sure why, but that's just a fancy name for it. Goes to 0. The thing is, we do need to let it go to 0 now because there's always a bit of random noise in the system. Because we always minimize a different gradient, and therefore even when you are at the minimizer, it will still continue moving because the minimizer of phi bar may not be a minimizer of all the phi i's or of any of the phi i's. So it will still move around the global minimizer. You want to avoid that, therefore you let the learning rate or the step size, what would you call it, go to 0 over time. Okay, what could possibly go wrong? So n could be large. Okay, we understood this. What is if phi bar is non-convex? So if phi bar is non-convex, the problem is if you just do gradient descent, you just get stuck in a in a settle point, or in a local minimizer. Local maximizer technically as well, but I mean you don't really get there, I think, so that's not too big a deal. But as soon as the gradient is 0 of phi bar, the algorithm ends. Independently of whether you found a minimizer, a global minimizer, a settle point, or whatever you found. Now, stochastic gradient descent doesn't necessarily get stuck, because you always have this like a bit of movement. So we'll usually just continue to move. But it's still not very efficient in a non-convex setting. And I just for the fun of it, I did a little example where, it's just a toy problem, where we try to minimize this function here on the right that has like 2 components. You could see it as like the most trivial neural network of all time if you want to, but this is just a handy problem. Obviously, this is not differentiable. Actually, there's a kink here, but let's just forget about that for a moment and just see what happens. So now, and the question really is, okay, I want to start sort of say like from like -1, and I want to get down to 0.5 because that's a global minimizer. And the question is kind of whether I get beyond 0 or whether I do not go beyond 0 and I just get stuck at 0. So that's the question I want to answer. And we just use gradient descent, starting from -1 with a reasonably small step size. Then we just get stuck at 0. So we just slowly converge to 0, and we don't jump over this point. I guess if the step size would be huge, then we would jump over the point, but then we probably wouldn't hope for convergence either. So this method will just not really work. Then I apply gradient descent, stochastic gradient descent, and actually here we are stuck in 0 for a really short time, but then we do jump over it and we do converge to the minimizer. It was quite exciting, but it's a stochastic algorithm, so we can't tell whether it's just a fluke or not. So I did it again, and it worked again. And then I did it once more, and then then it didn't work. Then we just got stuck at 0. And then I did it once more, and it worked. And I did it once more, and it didn't work. So it's kind of a bit, it's like 3 out of 5 not at work. Maybe it's not quite good enough for what we want to do. Obviously, it's a very simple setting, so this is not it's not a proof. But maybe this is like a hint that HG may not be the best thing to do in a non-convex optimization problem. Okay. Now let's talk a bit about classical mechanics, and let's see whether this can give us some idea on what we can do instead. And the idea really is, and it's kind of maybe the main idea of like half of my papers or so, is that it's sometimes useful to represent iterative algorithm like gradient descent or stochastic gradient descent by a continuous time process. Okay, an iterative algorithm is a bit like a discrete time process, and I personally prefer continuous time process. And it's not just me, it's many other people as well. So I do it particularly because discrete time process has some very specific behavior that may not be so important for us at the time of analysis. So what we say is like, okay, if we analyze this in discrete time, we may get really complicated step size conditions that we can never verify. But that are also maybe not so interesting. Because we're more interested maybe in quantitative behavior. Then there's some things we don't really see in discrete time. Like if you think of the deep learning problem from the beginning, so there you would see that the matrix C, the NASA problem, would see the matrix C is really, really badly conditioned, but only in the continuum we actually see how bad it is. Only in the continuum we actually see, the eigenvalue is converged to 0 at an exponential rate, so there's nothing you can do. So your favorite preconditioner will not save you here. And what is quite popular in the machine learning world somehow is to understand or analyze algorithms a bit like physical models, which is something I personally like as well. And there's kind of a lot of works on this, maybe even starting with like Rune Fatemi. Yeah, so maybe that's kind of where like mathematical imaging actually started, 1992. Yeah, which is a PDE that analyzes images or that reconstructs noisy images. Yeah. Okay. So what is the easiest example? Okay, the easiest example is gradient descent and gradient flow. Yeah, so gradient descent, if you kind of look at it and you remember like your, say like second year numerical analysis lecture, or maybe third year numerical analysis lecture, and you sort of let eta go to 0, yeah, then you might see, okay, this is just forward Euler for an ODE. Okay, this ODE is a gradient flow, and actually, I mean, if you think about it, then a lot of ODEs or a lot of PDEs as well, time-dependent PDEs, are just gradient flows. Yeah, so any the heat equation is just a gradient flow as well, for instance. Yeah. And what does this physically? Okay, it sort of says like we have a massless particle, like a photon would be a massless particle, and this ODE just describes the position of the massless particle. And yeah, and this is just like a force. Yeah, or here I call it like the velocity, but this is just a force that's acting on the particle, and that depends somehow on the gradient of this energy phi bar here. Okay, so far so easy. Now, for stochastic gradient descent, the whole story is a bit more difficult. Yeah, because what you can do is you can let eta go to 0 in stochastic gradient descent as well, and then like rescale the whole thing, and then you get this diffusion process here. Yeah, it looks a bit like this. So this in the beginning here is just our gradient flow, but then we get some like stochastic term as well. So it's kind of a bit weird because we let eta go to 0, but this depends still on eta. Yeah, so if you just let eta go to 0 in stochastic gradient descent, you will also just converge to the gradient flow, I think. I'm quite sure you do. But here you rescale sort of to retain some of the noise. And then the subsampling sort of becomes Gaussian because you have a CLT, and then you get this actually quite complicated term here. So in this case, we'll sort of say, okay, it's still a massless particle, but there are many other particles that sort of perturb this particle somehow. Yeah, so that's kind of where you get a Brownian motion from usually. Sort of say there's lots of interactions that you don't want to model one by one. Yeah, so you just model the interactions as noise. Yeah, and now this is what is called just like some kind of a particle drift. Exactly. Now, so I spent a lot of time in the last couple of years to sort of try to establish a different continuous time model for stochastic gradient descent. Because what I was, and obviously this is a much more popular one, the other one is just mine, but this is much more popular. But there's kind of one thing that I think is not so good about this one is that it doesn't subsample anymore. Yeah, so in stochastic gradient descent, the whole idea is we have only one data set at a time, but here you actually don't. Yeah, so here you have the whole data here in the drift. This is phi bar, and you subsample at like an infinitesimal speed. Okay, because you're Brownian motion, so there's randomness at every point in time. While in stochastic gradient descent, you actually kind of do a step and then you re-randomize. Yeah, you pick another data set, and then you do another step, you pick another data set, and so on. That's what I try to in this paper here try to establish is sort of this like piecewise ODE. Yeah, so we say, okay, so I of t is a continuous Markov process, so it looks a bit like this. Yeah, so it just jumps between the data indices. And theta solves this sort of piecewise ODE that has a randomized right-hand side. Okay, and it's always right-hand side is always constant, or it's like fixed. It's not a constant function, but it's constant for a certain time. Yeah, so while the process I is piecewise constant, and then we do a jump, and then the ODE sort of changes, and that's why you get this like sort of awkward-looking kind of process here. But that's, to me, reasons a lot better what stochastic gradient descent does. Now, and here we could now say, okay, this sort of models a massless particle in a randomly changing landscape, yeah, which maybe is not so natural, yeah, because why would the landscape randomly change? There are better biological explanations or better biological models for kind of where this happens. Yeah, so it's like a randomly changing environment to a population dynamics or so is something that's maybe a bit better than this. Um, so now there's some results from this paper that I just want to mention really briefly. So we sort of say we have just some continuous Markov process that jumps uniformly after waiting times that are just exponential 1. And so meaning just this is like a really simple, homogeneous, like nothing wild going on continuous Markov process that you just wait an exponential 1 waiting time, and then you jump to another place, and you pick the other places uniformly. Yeah, so that's the idea. You wouldn't need to do this, but this is just the simplest model you can do. And now there's sort of two settings we're interested in. The first one is constant learning rate. Yeah, so where this process I that we have here, yeah, so we just get this just as J, maybe with a time rescaling or so, yeah, with the constant time rescaling. And then we can prove a few things, yeah, so we can, for instance, show that the process theta here actually has a stationary distribution, yeah, which is nice because it sort of explains what happens when people don't let the learning rate go to 0, yeah, which is, I mean, I said in the beginning, don't do that, yeah, because I said, okay, to converge, you need to let eta go to 0, but people don't really listen to me when I say things like that, so, no, or not to me, but people kind of like to use constant learning rates, and they like to get into this like transient state in the end of the algorithm rather than getting to a point. And this actually shows here that there is such a transient state. So there is like a stationary state, maybe not the right words, but there is a stationary state in the end that we converge to, but it is a distribution. Yeah, it's not a point. We can also show that this converges to the gradient flow if this kind of switching rate goes to infinity. Yeah, or this, yeah, if we jump in this process infinitely fast, yeah, we will converge to the ODE. And if we let learning rate so that decrease over time, which would mean that these wait times become shorter, yeah, as time goes on, in a certain sense, then we do actually converge to the minimiser if things are nice and convex. Yeah, in both cases, things need to be nice and convex. Okay, so just as a quick recap of this paper here, those are some of the things we can show about this process. Okay. Now, if phi bar is non-convex, there's kind of one thing we can do, and it is actually give the particle some mass. Yeah, because if it has mass and the force is 0, then there's still momentum acting on the particle, and it will still kind of continue to move. And that's not very difficult actually to do that. Yeah, so we can have this what I call like underdamped gradient flow. I'm not sure anybody else calls it like that, but we do. And there we just get a different ODE. Yeah, it's now a second order ODE where x is the position, v is the velocity. Yeah, and then here m is the mass, alpha is the friction. Yeah, v is still the velocity, and it's just a different ODE. There's a lot of works on using momentum in optimization, probably starting with like Polyak and then like Nesterov, and also in continuous time. Yeah, so there is a whole community. There's like probably 25 papers or so just on but like just on this ODE system and properties of it in convex and non-convex optimization. Now maybe just what is interesting is maybe that if m is 0, we actually go back to the non-momentum case, yeah, because then this is 0, so this needs to be equal to that, and then you kind of just plug this in over here, and then you get back to the original ODE, which makes sense. Yeah, if there's no mass, then you should be back to the original system. If alpha is 0, then you would conserve energy in the system, which I claim is not that great in optimization, yeah, because you kind of want to stop at some point. Yeah, but so alpha, then I would say then it needs to be some friction. So just back to the example from before. Yeah, so this is now dynamic gradient flow with a really high friction parameter. Yeah, so this means essentially, okay, we now have mass, but we lose a lot of energy when moving because the friction is very high. But if we make it a bit smaller, then we do actually see that, okay, here we slow down, yeah, because there's like no force left, but then we do jump over it. We do roll over the edge, and we do eventually find the global minimizer. Okay, and if we sort of reduce this even more, the friction even more, then we actually see that, okay, now we also, it's like almost invisible now, not a 0 spot. Yeah, so we just like jump over it with a lot of confidence. But then what sort of happens is we have a lot of energy when we jump, so we kind of oscillate a bit until we converge. make this even smaller, we actually kind of jump back over it again and then need to kind of move for quite a while until we converge. And if we have no friction at all, then okay, then it's just a pendulum. Yeah, that is a bit like slightly nonlinear somehow, but so like an oscillator, like a harmonic oscillator. So yeah, that never stops. Yeah, so that's why I kind of advocate um, for having a positive friction. Okay. Now yeah, so like £5 million question is now, or that's like $7 million. I don't know, 8 million Canadian dollars. Not good at this. Um, is what do we do if phi bar is non-convex and n is large? And of course, like the idea of combining SGD with this momentum term, I mean, this is quite old. This goes back to a long time ago. And obviously, there's the other method which does this already, but in a much smarter way. That's seems to work really well in practice. There are like ways to use variance to reduce SGD. With momentum, there's like a lot of papers on this. Yeah. Now, what is interesting is that the analysis seems to be quite fairly scary. I mean, okay, nobody fully understands Adam, I believe. But there's this kind of like with interaction between these two things, like randomness and momentum, where both kind of get you close to where you want to be really quickly, because steps are so cheap and you kind of jump over things and so on. But then once you are close to the minimiser, so the SGD kind of still like hovers around because there's still like noise in the system, and the momentum still lets you move as well until energy is used up. And this just seems to be really complicated to analyze. And okay, our idea was to try to do this in continuous time. And that's what I will talk about in the next like 10-15 minutes now. Okay, so let's get to that. Obviously, what we do now is we look at this ODE, which is sort of the combination of piecewise ODE, or want to call it, is a combination of what I told you before about. So here we have this like subsampling process, in the functional phi, but otherwise we have this underdamped ODE, where q is the particle position, and p is the velocity. M is still the mass, alpha is the friction. There's now a few settings we're interested in. So still for this index process, we're still interested in constant learning rate and decreasing learning rate as well. So as before. And for mass, we're actually interested in two settings. We're interested in constant mass, as well as the sort of what I call like losing momentum. So mass going to zero. So actually converging to the original, or hopefully converging to the original stochastic gradient descent, as t goes to infinity. Okay, there's now two kinds of results that we're interested in. So because this process is so complicated, it's actually kind of hard to study this. So usually when something is complicated, we cannot really study it, but there's other things we understand sort of that are so surrounding it. We can often use those. And so our first idea was can we show limit theorems to the dynamic gradient flow? So this would be as stochasticity disappears. The stochastic gradient process, that would be as mass disappears. And the gradient flow, that would be as both disappears. So mass disappears and stochasticity disappears. Because we understand these three processes fairly well. So if we understand these limits, we might have an easier time understanding the stochastic gradient momentum process. The other thing we're really curious about is long-time behavior. Because in the end, we still want to optimize. It's optimization method. So we kind of need to know what happens as t goes to infinity with the distribution of this process. And then now is kind of the disclaimer that I mentioned before. So after having told you for 20 minutes we want to solve non-convex optimization problems, of course, we need convexity for all of these results, or for most of these results, actually, not all of them. So that's where the hypocrisy actually steps in. But I guess thank you for coming to my talk. Okay, let me just talk about this approximation really briefly, and I kind of made a nice figure. So because there's like now, and this like JMLR paper I really recommend it. So this was the preprint, but I recommend the paper came out last year. But this slide is about like 35 pages of that paper. It's like one slide because it's a lot of things, very technical. I'm sure you will enjoy reading it, but it's a bit difficult to kind of do this in a talk. So we need here, actually, we don't need convexity here, we just need smoothness, but we also don't show convergence here to a minimizer. So the first thing we can show is actually that as mass goes to zero, we do converge to the stochastic gradient process, okay? So if we don't have any mass, then we will be back to the massless setting. If the learning rate goes to infinity, or this goes to zero, sorry, the learning rate goes to zero, then we do lose the stochasticity and we do converge to the original underdamped ODE. Yeah, so we do converge to the normal ODE that has momentum. And if we let both go to zero, then we do actually find the original gradient flow again. Okay, which is already trivial, yeah, but this is like the sanity check, yeah. So this is like what we can then can use all other theorems in this paper. Okay, what is more interesting, maybe, or even more interesting, is this losing momentum setting, I think, where we actually see the momentum is kind of occurs in the blessing. I kind of mentioned this before, where we see because momentum allows us to get close to the minimizer quickly, but then prohibits us by there's still too much energy left, so we oscillate for like 4 weeks until we're kind of stopped. Yeah, until we're close enough to the minimizer. Now, if we reduce mass over time, we could provoke this stop much earlier. Now, it's a bit difficult to kind of imagine like a particle losing mass over time, but I mean, you could think of a pendulum that has like sand in it, and the sand is kind of going out, or so maybe that would be a right model. Yeah, so you actually lose weight, you lose mass over time, and therefore you kind of like swing less more quickly, not only due to friction. And that's like a really easy deterministic example that I did. Yeah, kind of minimizing my favorite function. So that's theta squared over 2. And we just start at 1 and with no velocity at all, and friction is equal to 1. Now, if the mass is equal to 1, then we do converge linearly, or like exponentially, to call it. Yeah. So that's like this like solid line here, where it's a bit weird because we do kind of we do find the minimizer whenever this sum here is actually hitting 0, which happens sometimes, but we don't stop, yeah, because there's still velocity. Yeah, but we still converge exponentially. Yeah, we still converge rather fast. Now the thing is, if we choose the mass to start at 1 and then reduce it at this algebraic rate, we do actually converge with this like squared exponential rate. Okay, so this is not like quadratically, so this is still much slower than Newton's method. Yeah, but this is still like superlinear. Yeah, so it's still much faster than linear convergence. Okay, that's kind of curious. And though we were wondering, okay, what happens if we now decrease learning rates and mass at the same time over time? Okay, and the thing is, we are able to show convergence here. It is a bit difficult to find a setting that actually works. Yeah, so you kind of need to so there's like beta as this function that rescales time in the index process, and m is the mass. Kind of need to figure out a way that they interact correctly, satisfy all assumptions. We did find a way, but what was actually weird is with our method we needed the setting to even show convergence at all. Okay, so our stochastic momentum process would not converge to a minimizer if we only decrease the learning rate. Maybe it does converge, but we just couldn't show it. But I actually want to persuade you that losing mass over time is an important thing to do, because that's kind of what we needed to prove convergence of this method, even for a simple convex problem. Okay. Let me just tell you a bit about implementation, and then I think we call it a day. So Sunny's in this process is quite easy. Actually, I mean, it is a bit strange to use these random time steps. So actually in the experiments, we just use deterministic time steps between them. I don't think it really matters. It matters kind of for the math a lot, because if you don't have these random time steps, the process is not Markovian. And then I'm a bit scared of non-Markovian processes, so I probably wouldn't work with it. What is a bit more difficult are these second order ODEs. Because I mean, we want to get the physics right. Yeah, so we want to choose a symplectic integrator. The thing is, it's not an energy conserving system, so technically you probably wouldn't need it. But then actually there are people that say, okay, even if the system doesn't conserve energy, you should still use a symplectic integrator. The other thing is we really want to choose an integrator that is able to discretize the ODE with a step size independent of the mass. Because for many integrators, that's not actually true. Yeah, so if you just look at the normal gradient descent with momentum or stochastic gradient descent with momentum, there you need to choose step size as a function, linear function of the mass. Yeah, and then we can't really let the mass go to 0 if we need to do that. So what we do is, yeah, and that would be symplectic Euler. Yeah, so what we do is we use a semi-implicit Euler. It looks a bit like this. So it's actually explicit in the gradient here, and it's implicit here and here. It doesn't matter so much that it's implicit because there's nothing is only implicit in like linear things, in like easy linear things. Yeah, so we can actually give an explicit formula for it, although it's an implicit method. What is actually nice here is, or what I think is nice, is if you let the mass go to 0, you do actually get the original gradient descent out again. Yeah, so if this mass here disappears, yeah, you just get gradient descent. Gradient descent back, normal gradient descent back. Yeah, so this is what we could show for the continuous system is also true for the discrete system. And now we did apply this to like some cipher 10 problem. I kind of said in the take-home messages before that we did it for convex optimization as well, which is true, but it's in the paper, it's not in the talk. And I mean, I think we're not claiming that this is the new method on the market, but we still want to see how it does. And actually, it is pretty good, especially when you have a really small mass. It's also pretty good when you reduce mass over time. Yeah, so this was actually worth doing. Like, okay, I mean, obviously this is not like industry standard 97% for Cypher 10, but it is a fairly simple CNN that we trained here. And yeah, as I said, I mean, we're not trying to compete with Atom also. Yeah, but as a sanity check, I think it was worth it to show that this works out and is actually helpful. Okay, just you've seen these already, so I'll not tell you about them again. Obviously, I mean, we started and we wanted to actually understand how Adam works. And obviously, you could just have an adaptive version of the stochastic gradient momentum process that would be similar to Adam. The analysis would be quite hard, and the application of that method would be even harder, I think. Yeah, so that's why we haven't done it yet. One thing I'm really curious about is I'm really interested in the stationary regimes of SGD. Yeah, because that's what people say is like implicit regularization, or what I say is implicit regularization. People call it like that as well. But I think that the stationary regime of SGD actually tells us about that. And then actually we do want to understand non-convex settings as well. Yeah, so actually it would be interesting to understand more about global conversion of these methods. And then, oh, I end with a photo of Manchester. Yeah, that's it. Thank you so much.